Welcome to the Deep Dive. Today, we're plunging into something really fascinating in AI, how we get artificial intelligence agents to, well, genuinely understand and interact with complex worlds.
Right, like mastering a tricky video game or maybe even eventually navigating the real world.
Exactly. And the big hurdle, it's a really significant one, is building AI that can quickly figure out how the world works. Its rules, cause and effect from just a little bit of experience, much like we humans do.
That's the core problem. An agent needs this internal world model to predict what happens next. Given what it sees and what it does, what's the outcome? This prediction is fundamental for, well, any intelligent planning or behavior.
Okay, so a good world model is absolutely key. For this deep dive, we're looking at a really interesting research paper, PoE-World, Compositional World Modeling with Products of Programmatic Experts, and some related notes. Our mission really is to unpack this PoE-World approach. What makes it new? Why is it potentially such a big step forward?
Right. And, to really appreciate PoE-World, it helps to quickly look at the older ways people tried to build these world models. There were kind of two main camps.
Okay, so the first one, probably the one most familiar to people, involves deep learning, right? Those big neural networks.
Precisely. Systems like Dreamer, for instance, they're incredibly flexible. They can learn complex patterns straight from pixels, very expressive models.
There's always a but.
The big but is data. They need huge amounts of training data. We're talking like hundreds of hours of gameplay in some cases. And even then, they can make predictions that just don't make physical sense, predicting an agent walking through a solid wall. So poor sample efficiency, issues with generalization, those are the key weaknesses.
Okay, so data hungry and sometimes predict impossible stuff. That's the neural net approach. What was the other main way?
The other way was more symbolic, representing the world's rules explicitly, maybe with code. More recently, people tried using large language models, LLMs like GPT-4, to actually write a program that describes how the environment works, like the World Coder system.
Interesting. Using an LLM to write the game's physics engine, basically. That sounds quite intuitive.
It does, and they can be more data efficient than the neural nets sometimes. Synthesizing code might need fewer examples.
So what's the catch there?
The big problem is scale. Trying to find one single program that captures everything in a complex environment, that search space is just enormous. It explodes combinatorially. So World Coder, it worked okay for very simple grid worlds maybe, but for something like Atari, it really struggled to build a comprehensive model because finding that one giant perfect program was just too hard.
Okay, so neural nets, flexible, but need tons of data, can be illogical, single symbolic programs, maybe data efficient, but can't handle complexity well. It feels like we're stuck between a rock and a hard place.
That's a good way to put it. Both approaches had these fundamental limits when you needed efficient learning for complex worlds. And that's precisely where PoE-World comes in. It offers a really different way of thinking about programmatic world modeling.
Okay, I'm intrigued. Tell me about this different approach. This is the core innovation, right?
Absolutely. The name gives it away. Product of programmatic experts. The key idea is, forget trying to learn one huge model. Instead, PoE-World learns hundreds, maybe even thousands, of small, simple programs.
Small programs, so little snippets of code.
Exactly like that. Think of each one as a tiny expert. Each expert only understands one specific little rule or causal law of the environment.
You have an example?
Sure. In a game, you might have one expert program that says, basically, if the player touches a skull, the player's state becomes dead. Simple. Another one might handle movement. If the action is left T and the player is on a platform, change the player's X velocity. Each one is a focused, deterministic piece of code for one interaction.
Okay, programmatic experts, lots of little specific rules, that makes sense. But what about the product of experts part? How do you combine predictions from hundreds of these things?
That's the clever bit. It's a specific mathematical technique for combining probabilities. Think of it like a community meeting. All these experts look at the current situation and the planned action. Each one calculates what its rule predicts might happen if that rule applies.
Okay.
Then the product of experts model combines these individual predictions probabilistically. It's not just averaging or voting, it multiplies their likelihoods together. So experts that strongly agree on a certain outcome really reinforce that possibility. And the system learns weights for each expert, basically, how much to trust each expert in different situations.
So if a bunch of relevant experts all point to the same outcome, the model gets really confident about that prediction.
Exactly right. They collectively shape the probability distribution over what the next state will look like. The system learns which experts are reliable for which kinds of changes.
And where did these little expert programs come from initially? You don't hand code thousands of them, surely.
No, definitely not. That's where program synthesis with LLMs comes back in. PoE-World uses models like GPT-4o mentioned in the sources. It shows the LLM examples of what happened in the game, like here's the state before, here's the action, here's the state after. And it asks the LLM to generate simple Python code snippets that could explain those observed changes. These snippets become the initial candidate experts.
So you feed it demonstrations, and the LLM proposes little rule programs.
That's the essence of it. And this whole approach, learning many small compositional programs instead of one big one, had some really significant advantages.
I can already see how breaking it down feels more manageable than finding one giant program.
It really is. The immediate win is modularity and compositionality. Learning lots of small programs is just a much easier search problem. That's why it can scale up. The sources mention PoE-World building models for Montezuma's Revenge with over 4,000 lines of synthesized code. Compare that to WorldCoder, which struggled past maybe 100 lines for simpler worlds.
4,000 lines of code representing the game's rules built from small pieces. That's impressive scaling.
And because it's modular, if some synthesized experts are wrong or irrelevant in certain situations, the system can learn to downweight or prune them. It avoids the kind of catastrophic failure you might get if your single big program has a bug.
That makes sense. More robust. So what are the big practical benefits we see because of this design?
Well, a huge one is data efficiency. Because it's synthesizing code, which has strong built-in assumptions about logic and structure, PoE-World can learn quite complex world models from very little data. The sources talk about using demonstrations that are just seconds long, maybe less than a minute of gameplay.
Seconds. To build a working model of something like Montezuma's Revenge, that's drastically different from the hours needed for neural nets.
It's a massive difference, and tied directly to that is generalization. Because it's learned these modular rules, it can often recombine them effectively in new situations.
So if you change the level layout.
Exactly. The paper showed this with alt versions of games like Pong and Montezuma's Revenge. Same basic rules, but different object placements, maybe slightly tweaked dynamics. PoE-World could often handle these unseen variations without needing any new demonstrations, just by reusing and recombining its learned expert programs.
So it's learning the underlying mechanics, not just memorizing specific levels.
That's the goal, yes. Learning the transferable rules. And the probabilistic combination handles stochasticity randomness in the environment naturally. It can also deal with partial observability, not seeing the whole game state, by keeping track of the history of observations and actions, which helps keep the individual expert rules simpler and learnable.
Okay, let's dig into the mechanics a bit more. How does this learning actually happen over time? And you mentioned something else, constraints.
Right. The learning is iterative. It starts with synthesizing those initial experts from a demo. Then, it optimizes the weights for each expert based on how well they predict observed transitions. Experts that don't predict well get their weights reduced, maybe even pruned entirely. Then, as the agent plays and sees new things, it can repeat the process. Refine weights, maybe synthesize new experts if it encounters something unexpected. It's an online learning process.
So it keeps improving its understanding as it interacts. What about those constraints you mentioned?
Yes, hard constraints. These are another crucial component, also learned, often synthesized by LLMs. But unlike the probabilistic experts, these are deterministic rules. Think of them as absolute physics checks or filters.
Filters. How do they work?
While the experts give you a probability distribution over possible next states, the hard constraints step in and say, okay, any of these predicted states that violate fundamental physical laws are impossible. Throw them out.
So they act like a reality check on the probabilistic predictions.
Exactly. The paper gives examples like, if the agent is supposedly standing on a platform, its feet pixels must align with the top of the platform pixels. Or, if it's climbing a ladder, its body must be centered on the ladder. These things have to be true.
And why are these needed? Don't the probabilistic experts learn this stuff?
You'd think so, but the researchers found these hard constraints were absolutely vital, especially for long horizon planning. The probabilistic model might predict states that are mostly right, but maybe slightly physically off in subtle ways.
Okay.
Over just one step, that tiny error might not matter much for prediction accuracy. But if you're planning dozens or hundreds of steps ahead, those tiny physical impossibilities accumulate, and your plan falls apart because it's based on simulating impossible futures. The hard constraints act as damage control, ensuring the plan's sequences stay physically plausible.
Ah, I see. They keep the long-term simulation grounded in reality, making planning feasible, even if the probabilistic model isn't perfect.
Precisely. They make the learned model usable for actual decision-making over longer timescales.
So, speaking of decision-making, how does the agent actually use this PoE-World model to achieve goals?
Two main ways. First, as we touched on, it's a fantastic simulator for reinforcement learning. The agent can basically dream or practice millions of interactions inside its learned model, much faster and cheaper than interacting with the real environment. This massively speeds up learning a good policy.
Right, learning from imagined experience.
Exactly. But the other, perhaps more direct use is planning. With a model that predicts the future, you can search through sequences of actions to find one that leads to a desired outcome.
But planning in these complex Atari games like Montezuma's Revenge, finding the right sequence of hundreds of joystick moves sounds incredibly difficult.
It is. Brute force search is hopeless. So, the paper paired PoE-World with a clever hierarchical planner.
Hierarchical, how does that work?
It breaks the planning problem down. There's a high-level planner that thinks abstractly, maybe about navigating between key objects or locations, like get the key, then go to the door.
Okay, big picture steps.
Right. Then, for each of those abstract steps, a low-level motion planner takes over. It uses the detailed PoE-World model to figure out the specific sequence of actions needed to achieve that smaller sub-goal. It might use search techniques like Monte Carlo tree search, or maybe just greedy search with sticky actions, repeating an action for a few frames, which is common in Atari.
So it's like plan the chapters, then write the paragraphs.
That's a great analogy, and the results they got were really strong. PoE-World, combined with this hierarchical planner, significantly outperformed baseline methods like standard RL algorithms, PPO, LLM agents without world models, React, and even the previous symbolic approach, world coder with a planner.
Especially in those low data situations.
Exactly. And on the generalization tasks with the altered game environments, the paper highlighted that PoE-World was the only method tested that could achieve any positive reward in Montezuma's Revenge when trained on very limited data. That's a notoriously hard benchmark.
That really underscores the power of this compositional model for efficiency and generalization.
Yeah.
You also mentioned earlier some connections to human cognition.
Yes, and this is quite thought-provoking. The whole architecture building complex understanding by composing lots of simpler, specialized pieces resonates with some theories about how our own minds might work. The idea of the mind as a community of interacting agents or modules.
Interesting. Like different brain areas specializing.
Or even just how we combine basic concepts to understand complex things. The way PoE-World recombines its learned rules to handle new situations feels analogous to how symbolic thought works, enabling flexible generalization.
And the planning part, too.
Yes, the hierarchical planning, thinking abstractly first, then refining the details, focusing on interactions with objects that aligns well with studies on how humans seem to segment events and plan actions hierarchically.
Even the idea of learning rules as little programs.
There's cognitive science research suggesting that human concept learning might involve something like learning mental programs. So PoE-World isn't just clever engineering. Its structure taps into some deeper ideas about how intelligence itself might be organized.
So recapping the core idea, PoE-World offers a powerful new way to build world models by learning and combining thousands of small programmatic rules. This makes learning highly data efficient and allows for strong generalization, potentially mirroring some aspects of how we understand the world.
That's the essence of it. Compositionality through these programmatic experts tackles the key weaknesses of previous approaches, especially for complex environments.
What about limitations? What did the paper acknowledge?
Well, a key one is that it currently works with symbolic inputs, object lists, states, etc., not raw pixels directly. Translating this approach to end-to-end learning from vision is still an open challenge.
Okay, so it needs a perception system first.
Right. And the work focuses very much on the world model. You still need other parts for a complete agent, like exploration strategies or learning what goals are rewarding.
It's a critical piece, but not the whole picture yet.
Exactly. But the form of the learned model, this collection of programs, leads to some really exciting future possibilities mentioned in the sources.
Well, like what?
Well, think about it. The AI's understanding of the world is literally represented as code. a big library of Python functions, essentially. So the researchers propose applying techniques from software engineering, things like program analysis and software testing, directly to the AI's world model.
Wait, using debugging tools on the AI's internal knowledge?
Exactly. You could potentially analyze the learned code to find inconsistencies, gaps in knowledge, areas where the model is uncertain or makes weird predictions, effectively finding bugs in the AI's understanding.
And how would that help the agent?
That analysis could then guide the agent's exploration. Instead of just wandering randomly, the AI could design specific experiments or tests to run in the environment, gathering the exact data needed to fix the identified bugs or fill the knowledge gaps in its internal model.
Wow. So the AI could actively diagnose its own misunderstandings and intelligently seek out the information needed to correct them. That's much smarter than just random exploration.
Precisely. It moves towards a much more targeted and efficient way of learning and refining understanding, driven by introspection on its own programmatic knowledge.
That is a seriously cool idea. Applying software verification to learned world models. It really reframes how we might think about improving AI competence. So, PoE-World feels like more than just an incremental improvement. It's a potentially foundational shift in how we build agents that understand complex dynamics.
It definitely offers a compelling alternative, emphasizing structure, compositionality, and the power of programmatic representation.
And that final thought, using tools from programming to help an AI debug its own understanding of reality, that's something to chew on. It blurs the lines between learning and programming in a fascinating way.
It certainly opens up new avenues for research.
Well, thank you for walking us through this fascinating approach. That was a great deep dive into PoE-World.
My pleasure. It's exciting work.